Modern manufacturing operates under immense pressure. Facilities must hold tighter tolerances and adapt to shorter product life cycles than before. But physical floors remain rigid. When you stop a live production line simply to trial a new fixture or test a different robot path, you are actively burning runtime. Every idle minute directly subtracts from overall factory output. Relying on manual teach-pendant programming means engineers must physically jog the robot from point to point. This method not only inflates commissioning hours, but it exposes the hardware to the risk of accidental, destructive collisions on the shop floor. As product designs iterate more frequently, these manual updates compound. A line that requires physical intervention for every geometry change quickly becomes unsustainable to operate. The traditional reactive workflow of developing paths on the shop floor mathematically limits throughput. It represents a bottleneck that prevents facilities from scaling to meet modern production targets. To solve this, we use a digital twin. A static 3D model shows what a machine looks like. A true digital twin is a living representation. It continually updates, reflecting the physical system's exact behavior, driven by real-time data and control logic. RoboDK is a simulation platform specifically engineered to generate these virtual environments. It provides the tools required to build credible, deployable replicas without tying up physical hardware. To see how this actually works, we need to build a production-grade digital twin from scratch and deconstruct its operational layers, one by one. Moving the iteration process off the physical floor creates a virtual sandbox where configurations can be refined without jeopardizing active production hardware. The first layer is geometry. We import raw CAD data for fixtures, parts, and tooling, building the virtual work cell to mirror the engineering design. Next, we align coordinate systems and reference frames across the cell, locking in exact spatial relationships. With the environment set, we select the hardware. RoboDK maintains a library of over 750 robot models, allowing engineers to evaluate multiple vendor options for a specific layout. This compatibility prevents vendor lock-in, letting you compare reach across brands before committing. Once placed, we define the tool center point. Attaching an end-of-arm tool, like a weld gun, establishes the exact point the robot calculates its reach against. We then input payload assumptions. The software requires the precise mass and mechanical inertia of the part being handled to calculate accurate movement. These physical parameters force the virtual environment to respect the actual mass and spatial footprint of the real world. This exact geometric and hardware foundation is a strict prerequisite. Without it, any subsequent motion logic will be mathematically flawed. Layer 2 applies accurate kinematics, where offline programming begins, translating theoretical design into robotic movement. Path generation is dictated by process parameters. We input well tolerances, turning a continuous curve into a strict sequence of numerical targets. A generated path might look perfectly efficient on a screen, but that does not guarantee the mechanical joints of the real robot can physically achieve it without hyperextending. The primary obstacle here is a singularity, a specific configuration where the robot's joints align in a way that mathematically paralyzes its movement or forces an erratic, unpredictable swing. To counter this, RoboDK actively analyzes the kinematic and automatically adjusts wrist configurations mid-motion, ensuring the trajectory remains predictable as it bypasses those dead zones. Using the established reference frames, engineers configure designated approach points and safe zones, building the strict boundaries the robot will use to enter and exit the work area safely. The system then runs a comprehensive reach study. This confirms that every single target point within the sequence can actually be reached by the chosen hardware. Simulating these reach constraints early reveals if the robot base needs to be shifted 2 inches to the left, or if a fixture is positioned out of range. Locking in mechanical feasibility in the software ensures these layout corrections cost nothing, rather than forcing expensive rework after the hardware is bolted to the factory floor. Precise kinematic modeling ensures that the programmed motion respects the mechanical constraints of the hardware before it ever reaches the controller. Layer 3 introduces system validation. Here, we analyze how the hardware navigates the tight physical clearances around complex part nests and safety guarding. The platform uses geometry-based collision detection algorithms to actively scan for any physical interference between the moving tool, the robot arm, and the surrounding environment. When a collision is detected, engineers do not have to rewrite the entire program. They simply adjust the tool's approach angle, and the system instantly recalculates a new safe trajectory. If an approach is completely blocked by a clamp or fixture, entire machining operations can be quickly reordered in the virtual space to bypass the clearance issue entirely. With a safe path confirmed, we execute the full sequence to simulate cycle time, providing a highly accurate measurement of the system's true mechanical throughput. This allows teams to measure takt compliance without touching a stopwatch. The simulation isolates exactly which motion segments are creating operational bottlenecks. This chart displays the resulting performance data. From here, you can adjust acceleration parameters and motion blending, testing different speed profiles to shave seconds off the baseline time and increase overall output. Virtual validation systematically eliminates physical clearance failures and sequence inefficiencies, ensuring the cell operates at maximum capacity before launch. A robot's physical movement is dictated by the logic commands it receives from the broader automation stack. Layer 4 integrates this external control logic. This requires integrating the Programmable Logic Controller, or PLC. This maps digital signals to the robot, reflecting the station's physical interlocks and readiness states. Signal-driven sequencing ensures the digital twin behaves like the real cell, pausing and resuming operations based on complex manufacturing variables, not just a static timer. We deploy virtual sensors to emulate critical perception logic. When a digital part intersects a beam, it confirms part presence, satisfying the logic needed to trigger the next sequential movement. This logic extends outward, pairing the robot with external externation devices like rotary part positioners and linear tracks. It also enables the synchronization of the robotic arm with external material handling systems. A conveyor belt introduces a new part, and the arm executes its exact handling sequence in perfect time. Validating this multi-system timing across different automation brands ensures that all components communicate flawlessly, eliminating unexpected logic failures during physical commissioning. This alignment of mechanical simulation and control logic provides a predictive model of the entire cell's behavior. The final bridge from virtual simulation to shop floor reality is the post-processing phase. Through RoboDK, the exact validated offline motion paths are translated directly into native executable programming code formatted specifically for the targeted hardware controller. This code is then deployed immediately to the real robot. There is no need for tedious manual point teaching on the floor. This yields a measurable operational return. Facilities that shift path iteration into this offline environment routinely see a 30 to 50% reduction in total programming time. This operational speed directly lowers commissioning hours and improves project delivery predictability across the entire facility. Long-term, the digital twin is integrated upward into the factory's manufacturing execution system, allowing for continuous, centralized performance monitoring. By comparing the established baseline of the twin against live production data, teams can identify unexpected dwell times, quickly diagnose throughput anomalies, and implement predictive maintenance. RoboDK moves simulation beyond a one-time check. It provides a repeatable asset, enabling manufacturers to respond to product changes with agility.